Cell 1. In this cell, we're diving into why pulling data from SQL Server and utilizing Python for error detection, particularly spelling errors, is crucial for effective data management. Understanding these motivations is key, as they highlight the fundamental issues that arise from poor data quality and the significant repercussions it can have on various operations within an organization. First, let's consider the impact of misspellings on data integrity. When individuals or companies are recorded with variations in spelling, like John Smith versus John Smith, it creates duplicates in the database. These duplicates can severely disrupt database joins and compromise the accuracy of customer 360 views, which are essential for understanding customer relationships thoroughly. Next, think about how typos contribute to errors in downstream analytics. Misnamed entities inflate the number of unique categories, leading to distorted counts and added noise in the features used for analysis, which in turn affects the reliability of dashboards, forecasts, and the performance of machine learning models. Each of these inaccuracies can lead to misguided decisions based on faulty data. Operational efficiencies also suffer when bad spellings cause issues like failed mailings, misrouted shipments, or incorrect invoices. These errors not only frustrate customers, but also lead to increased workload and confusion for support teams. Addressing these concerns directly impacts the bottom line. Additionally, organizations are increasingly focused on data quality and governance scores. It's essential to track completeness, validity, and consistency, and spelling anomalies represent a tangible, measurable issue that can be monitored over time. We can't overlook the potential for identifying fraudulent behavior. Fraud rings often exploit slight variations in names or addresses to avoid detection. By flagging these near duplicates, organizations enhance their investigative capabilities. Standardizing reference data stands as another significant benefit. Cleaning high-impact fields like city names, vendor names, and product descriptions enables more effective normalization and master data management. Incorporating automation into this process can transform how organizations identify and rectify spelling errors. Instead of relying on humans for ad hoc reviews, Python can be employed to systematically score the likelihood of misspellings, rank them, and generate reports for data stewards on a regular basis. Finally, the insights gained can lead to a feedback loop that prevents future errors. This means putting robust input validation rules in place, creating drop-down lists, and establishing fuzzy match warnings during data entry. Such measures would not only enhance data quality, but also provide targeted training to teams responsible for entering data. As we move into the next cell, we'll likely begin implementing these concepts, focusing on the technical details of extracting data and starting to apply Python's analytical capabilities to catch these spelling discrepancies effectively. Cell 2. In this cell, we are setting up the essential components for accessing and analyzing data from a SQL Server database. We start by installing necessary packages, which lay the groundwork for our data manipulation tasks. Here, we utilize libraries like pandas for data handling and SQLAlchemy for managing database connections. This combination is powerful, as it enables us to pull in structured data from a relational database seamlessly. First, we specify our database connection details, starting with the server name, the specific database, and the driver used for auditable connections. These parameters are crucial, as they inform our connection string how to talk to the database. The use of trusted connection yes indicates that we are leveraging Windows authentication, making it often more straightforward to establish a secure connection without embedding credentials in the code. Next, we create the connection engine using SQLAlchemy. This engine acts like a bridge between our Python environment and the SQL Server database, allowing us to perform SQL queries directly. In this case, we're interested in fetching customer data from the AdventureWorks database. The SQL query itself selects the top 1,000 customer records, extracting various attributes like customer ID, name style, title, and contact information. These fields are crucial for understanding customer demographics and their interaction with the business. After formulating our query, we use the pd.readSQL function to execute it and load the resulting data into a pandas data frame. This function not only pulls the data, but also formats it neatly, making it easier to manipulate in subsequent analyses. The result is stored in the variable df, which we'll be examining closely in later steps. It's worth noting that while this setup is straightforward, learners should ensure that the server's name and audibc driver match their local setup. Small discrepancies can lead to connection errors. As we proceed, we will explore this data in more depth, allowing us to derive insights that help us understand customer behavior and business performance. In the next cell, we will delve deeper into data exploration and visualization, building on the foundational work we've laid here. Cell 3. In this cell, we're establishing a connection to a SQL Server database using provided credentials and retrieving data into a pandas data frame. This step is crucial because it allows us to interact with our database and analyze the data directly within our Python environment. The first part of the cell focuses on setting up the connection string. Here, we define key variables such as the server name, the database name, and the user credentials. It's important to note that while this snippet uses explicit username and password credentials, in a production environment, you might want to consider more secure methods such as Windows authentication or environment variables to protect sensitive information. After defining these variables, we construct the connection string by specifying the driver, server, database, username, and password. This connection string is essential for the SQLAlchemy engine, which will manage our database interactions. Once we have our connection string, we create an engine using SQLAlchemy's createEngine function. This step is where the connection to the SQL Server is established, allowing us to execute SQL queries and retrieve results in a format that's easy to work with in pandas. The final step involves executing a SQL query against our database by using the pd.readSQL function. This reads the results of the query directly into a data frame. Calling df.head then provides a quick glimpse of the first few rows of data, giving us insight into what we're working with. As we move forward, the next cell will likely build on this foundation by performing analyses or transformations on the data we've just retrieved. This could include filtering specific records or aggregating the data to extract meaningful insights. Cell 4. In this cell, we're focusing on a more nuanced approach to detecting misspellings by leveraging probability scores derived from various signals. This method is essential because it allows us to differentiate between genuine misspellings and names that might be acceptable variations, such as Sally and Sally. The process outlines several key scoring signals that help us evaluate the likelihood of a misspelling. First, we consider the dictionary likelihood, which looks at the usage of common English words. If a word is absent from our reference dictionary, it raises a red flag about its validity. The word.frec library not only provides the frequency of common words, but also aids in establishing a baseline for what constitutes normal usage. Next, we assess edit distances, which quantify how many single-character modifications, like insertions, deletions, or substitutions, are needed to transform a misspelled word into a valid one. For instance, the word Sally is one edit away from Sally, highlighting a potential concern if Sally is commonly used. By employing the rapid fuzz library, we can quickly measure these distances and make informed decisions. The third signal pertains to field-specific vocabularies. Here it's crucial to compare a given name or term against a trusted list, such as those for cities or product codes. This ensures that our evaluation aligns with the specific context in which the data is being used. Lastly, we introduce an exception handling mechanism for name variants. This can involve utilizing a list of historically accepted names, or even a whitelist of terms we intentionally choose not to flag. The key insight here is that if a term frequently appears in our dataset, its probability score might remain low, suggesting that it's likely valid. As we move forward, the next cell will likely build on this framework, integrating these various scoring methods into a cohesive function capable of efficiently evaluating text against these parameters. This will enhance our overall ability to clean data and improve accuracy in any subsequent analyses. Cell 5. In this cell, we're taking crucial steps to set up our environment by installing necessary packages that will enhance our text processing capabilities. This is an essential part of ensuring our code runs smoothly, particularly when we delve into tasks like measuring text similarity or checking for spelling errors. To start, we import the sys module, which allows us to interact with the Python runtime environment. This is particularly useful here, as we'll execute a command that utilizes the current Python executable to install a couple of packages, specifically word.frec, rapidfuzz, and pyspellchecker. Each of these libraries serves a unique purpose. Word.frec provides frequency information for words in various languages. Rapidfuzz offers powerful string matching functionalities, and pyspellchecker aids in correcting misspellings. By running this command, we effectively make a call to the package manager, ensuring that the latest versions of these libraries are installed, which might be necessary if we want to leverage the most recent features and bug fixes. After this installation step, there's a critical note about restarting the kernel. This is particularly important because some installations won't be recognized until we restart the environment, which clears any cached information and ensures that our new packages are correctly integrated. This cell sets the foundation for what's to come, allowing us to perform advanced text processing tasks confidently. Without this installation, we might encounter errors down the line when we attempt to invoke functionalities from these libraries. So now that we've prepared our environment, the next cell will likely involve an exploration of how to use these newly integrated packages to analyze text or compare strings effectively. Cell 6. In this cell, we're laying the groundwork for a misspelling probability score, which is pivotal for understanding text accuracy and improving user input quality. We achieve this by focusing on tokenization and scoring utilities that will help us process text effectively. The code begins by importing necessary libraries, namely RapidFuzz, which is great for fuzzy string matching, and RE, which is essential for regular expressions. We've also established a set of common stopwords, which are typically less informative and will be filtered out in later stages. This ensures that our analysis prioritizes meaningful vocabulary. Jumping into the functions, the first is tokenize, which takes any given text and returns a list of tokens. It does this by finding matches based on our regular expression, which captures alphabetic characters and apostrophes. The incorporation of lowercase conversion within this function ensures that our tokens are consistent. Next, we move on to filtered tokens, which builds off the tokenize function. This function filters out tokens that are either too short or part of our predefined stopwords. As a result, it helps refine our dataset by focusing only on tokens that are at least 3 characters long, maximizing relevance for our analysis. The third function, build vocab from column, is particularly significant for creating a vocabulary that is specific to the dataset we're working with. It takes in a data frame and a column name, counting the occurrences of each token. By using a minimum count parameter, we guarantee that only tokens appearing frequently enough are considered valid. This helps avoid noise in our vocabulary. A crucial takeaway here is the importance of assumptions about the data. For instance, our approach hinges on the expectation that common misspellings or variations will often be among the frequently occurring tokens. As we wrap up this cell, we can look forward to leveraging this misspelling scorer in the next steps. This will likely involve assessing the accuracy of tokens against our whitelisted vocabulary, allowing us to refine our understanding of text quality even further. Cell 7. In this cell, we're diving into a function designed to assess the probability that a given token or word might be a misspelling. This is particularly useful when processing text data and cleaning up any inaccuracies in spelling, which can significantly affect the quality of analysis and insights. The function methodically evaluates a few factors that contribute to determining how likely it is that the input word is indeed misspelled. At the start, the function normalizes the token to ensure a consistent comparison by converting it to lowercase. It considers a length check, returning a score of 0 for any token that's short, specifically words with 2 or fewer characters, because there isn't enough context to make a reliable judgment. This is a smart move, avoiding unnecessary false positives on very short inputs. The function then checks against a known vocabulary list, which consists of valid words, ensuring that if the token is known and valid, it's automatically deemed non-misspelled. If the token isn't known, the code evaluates whether it appears frequently in the user's dataset. This helps account for unusual names or terms that might not be widely recognized, but are indeed valid in a specific context. A crucial step is the use of Zipf's law, where the frequency of the word in the English language plays a role in estimating its misspelling risk. By retrieving a score that indicates how common or rare a word is, the function computes a corresponding risk score. Common words carry low risk, while rare ones are treated with higher suspicion, setting the stage for a deeper investigation. If the token is rare, the function gets even more sophisticated by finding similarities between it and more frequently used words. It checks matches among candidate words and boosts the risk score based on how closely related they are, especially when the candidates are quite common in the dataset. This approach combines linguistic analysis with statistical findings, allowing for nuanced decisions about spelling. In addition, if the token appears just once in the dataset, the risk score is slightly boosted, reflecting that its rarity within that specific context adds to the likelihood of it being a misspelling. Overall, the risk score is carefully clipped to ensure it stays within a valid range, so it can be interpreted easily. This function is an interesting intersection of language processing and data analysis, enabling more accurate text cleanup as we move forward. In the next cell, we'll likely apply this misspelling probability assessment to real tokens in a dataset, establishing a clearer understanding of how effectively this scoring system works in practical scenarios. Cell 8. In this cell, we're diving into the scoring of tokens extracted from one or more text columns in our dataset, which is particularly important for identifying potential misspellings. This process allows us to create a comprehensive understanding of the text data's quality and consistency, focusing on names and company names in our data frame. The logic unfolds as we first build a vocabulary from the specified column, filtering out common terms that might skew our analysis. This step is crucial because it ensures that we are working with a list of relevant terms, enhancing our ability to identify errors. Next, we iterate through each entry in the chosen column, converting missing values to blank strings and processing each entry as a string. With each token extracted, we apply our misspell probability function, which compares the token against our dataset's vocabulary and a potential known list of correctly spelled words. An essential detail here is the threshold for token length. We only focus on tokens that satisfy the minimum length requirement, as shorter tokens are often less informative. The results, wrapped up in a structured format, include the index of the row, the column name, the token itself, its misspelling probability, the original value, and the count of that token in the dataset. This output is then compiled into a data frame, sorted by the misspelling probability. This sorting prioritizes the tokens that require our attention the most, helping us focus on the most suspect entries at a glance. After scoring both names and company names, we concatenate the results and display the top and bottom entries to understand our findings comprehensively. As we move forward, the next cell will likely build on these insights, potentially exploring how we can leverage this misspell analysis for further data cleaning or profiling tasks to ensure that our dataset is as accurate as possible. Cell 9. In this cell, we're refining our approach to identify companies more accurately by minimizing false positives. This is crucial because accurately matching company names can significantly improve our data quality and reliability in subsequent analyses. To achieve this, we're leveraging a list of known company names drawn from our SQL database and enhancing our tokenization process. Starting with the data retrieval, we first extract distinct company names from the AdventureWorks database, converting them to lowercase for consistency. This step is essential because it standardizes the names and helps ensure that comparisons are made fairly without case sensitivity issues. Next, we're constructing a set of potential company tokens. This involves iterating through a vocabulary of company names and applying a tokenization function to filter out relevant tokens. By collecting these tokens into a set, we eliminate duplicates, making our dataset cleaner and more manageable. Once we generate our list of company token candidates, we sort them for easier analysis. The output at this stage provides not only the count of unique tokens, but also showcases the first few entries. It's important to note that a small misstep in tokenization could lead to missing a valid company, or generating misleading matches. Therefore, learners should pay close attention to the filtering process. Afterward, we delve into scoring our company tokens against the provided data frame, where we evaluate how likely a name in this data frame corresponds to our known vocabulary. This scoring is pivotal as it helps flag suspect company names that may not align with our known dataset. The output presents the top potential mismatches, allowing for manual review where necessary. As we look forward, the next cell likely builds upon this refined token scoring by introducing methods to enhance our matching process further. We'll explore strategies to improve accuracy even more by incorporating additional layers of information, paving the way for smarter data integration. Cell 10. In this code cell, we're focusing on enhancing the accuracy of company names and first names by generating candidate corrections based on frequently occurring tokens. This process is essential because it helps us identify potential misspellings or variations in names, which can significantly improve data integrity and ensure more reliable analyses down the line. The logic starts with building sets of tokens from the company names and first names present in our dataset. For the company names, we filter and analyze tokens that have a minimum length of 3 characters, while we handle first names slightly differently, allowing all tokens longer than 3 to be included. The reasoning here is straightforward. We want to ignore short, potentially unhelpful tokens that could dilute our results. As we collect these tokens, we then count their occurrences to determine which ones appear frequently enough to suggest potential corrections, specifically looking for tokens that show up at least 5 times. Once we have our candidate lists, the function for suggesting corrections utilizes the fuzzy matching library to find the closest match for a given token. This is important for catching misspellings or variations, making sure that we only recommend corrections when they meet a certain confidence threshold. The results will not only include the suggested fix, but also a similarity score, which tells us how closely the suggestion matches the original token. Next, we apply this correction logic to our dataset of potentially misspelled names. The code prepares two masks for filtering entries, specifically for company names and first names, allowing us to apply the suggestion function selectively. The final output showcases the top entries along with their suggested fixes and corresponding similarity scores. It's important to recognize that this technique is versatile. We could focus solely on company names or first names by adjusting our filters. Moving forward, the next cell might build upon this correction feature, perhaps adding a layer of validation or further analysis on the corrected names to ensure even higher data fidelity. Cell 11. In this cell, we explore an alternative method for suggesting corrections to possible misspellings in company names and first names from our dataset. By leveraging the capabilities of the counter class from the collections module, we can analyze token frequencies, which play a crucial role in helping us understand how often certain names appear relative to others. Initially, we compute the frequency of tokens in both the company name and first name columns of our data frame. This is important because it allows us to prioritize suggestions based on how common a name is within its respective context, enhancing the accuracy of our recommendations. The filtered token lists are generated through list comprehensions, processing the non-null entries of each column to prepare for the subsequent analysis. Next, we define a function called suggestCorrectionSmart. This function takes a token and a list of potential candidates, along with a frequency map of tokens. Its purpose is to intelligently suggest the best correction for a given token. It first transforms the token into lowercase for uniformity, then uses fuzzy string matching to find the closest candidate. If a matching candidate is identified, the function checks if it's significantly more common than the original token, and whether its similarity score meets a defined threshold for acceptance. The main logic flows smoothly as we create a subset of our suspect's data frame, designated to hold the top entries we want to examine. We establish masks for identifying whether the tokens belong to the company name or first name columns, updating the suggested fix and similarity columns based on our smart suggestion function. This targeted approach ensures that only relevant suggestions populate our data frame. Moving forward, the next cell is likely to build on this foundational structure by applying the suggested corrections to address inaccuracies in our dataset. We aim to refine our data results further and evaluate the effectiveness of these correction strategies in enhancing data quality or a subsequent analysis step. Cell 12. In this cell, we're diving into the concept of probability as it relates to our analysis. This is particularly important because it helps us understand the underlying principles of how we assess the likelihood of certain tokens appearing in our dataset. We aren't just dealing with pure mathematical probabilities here. Instead, we're working with a risk score that's been scaled between 0 and 1. To break this down, the risk score we generate combines several key factors. First, we consider how common a token is in the English language, which we measure using an external resource that reflects word frequency. Then, we assess the token's rarity within our specific dataset, which helps us understand its prominence or lack thereof in the context we're analyzing. Lastly, we take into account the edit similarity, essentially how closely related the token is to more frequent ones. This step allows us to capture nuances that might otherwise go unnoticed. Throughout this process, it's crucial to remain aware of our assumptions. For instance, if a token appears frequently in English but rarely in our dataset, the risk score will reflect that disparity. Similarly, tokens that are similar to commonly used words may carry a different weight in our scoring system. These elements underscore the importance of context in our analysis. As we move to the next cell, we'll build upon these foundational concepts. We'll likely apply this risk scoring method to evaluate specific cases or tokens, deepening our understanding of how they fit into our broader study. This progressive development will enable us to draw more nuanced conclusions that are representative of the data we have gathered. Cell 13. In this cell, we're creating a data frame that simulates a realistic scenario involving various business activities. This is important because managing and analyzing such data can help organizations understand their operations better, particularly when it comes to handling names and descriptions, which are often complex. The structure of the data is straightforward. It includes records that capture different business processes along with their respective categories and statuses. Each entry is stored as a dictionary, which allows for an organized representation of diverse descriptions, from customer support issues to finance-related discrepancies. By using a random seed for reproducibility, we ensure that any subsequent analysis can yield consistent results, which is crucial when testing and validating our models. Within this data frame, we can notice a mix of entries, some of which feature correct spellings, while others include realistic misspellings and typos. This mix is essential for testing how well our system can handle variations in textual data. The records are segmented into categories like support, finance, and logistics, helping us understand the nature of each entry and allowing for targeted analyses. At this stage, learners should be aware of the significance of including such errors in the dataset. They will need to think about how to clean and pre-process this data for analysis. For instance, handling inaccuracies in spelling is pivotal in ensuring that insights drawn from this data are reliable and actionable. The expected output of displaying the tail of this data frame will provide a glimpse into the final entries of our dataset, giving a better understanding of the structure. This visual representation can help guide users in grasping the kind of data they'll be working with. Moving forward, the next cell will likely delve into methods for cleaning this data, thereby preparing it for further analysis. This foundational work is crucial as we aim to extract meaningful insights from real-world datasets. Cell 14. In this cell, we're diving deep into analyzing text data by building a comprehensive framework for detecting and addressing misspellings in descriptions and categories. This is crucial because accurate text data can significantly enhance the reliability of any data-driven decisions and insights. To kick things off, we import several essential libraries, such as pandas for data manipulation and NumPy for numerical calculations, while also setting some display options to ensure we can see all available rows and columns in our output. Our approach to text analysis starts with tokenization, where we define a pattern to identify valid words and filter out common, less informative stopwords. This means we're focusing on meaningful content that carries more significance for our analysis. Next, we have functions designed to build frequency counts of the relevant tokens appearing in specified columns. By utilizing the counter class, we can efficiently tally how often each token appears, which sets the stage for determining which terms are common enough to trust and which might indicate potential spelling issues. The functions also allow us to generate a list of candidates for correct spellings based on their frequency, ensuring that we have a solid foundation for our subsequent analysis. A critical part of the cell involves calculating the misspelling probability for each token, providing insight into how likely a token is to be misspelled based on its length and rarity. This scoring accounts for the fact that shorter tokens are often more ambiguous, hence we weigh them differently. Following this, we employ a smart suggestion function that analyzes tokens against this candidate list, linking misspellings to contextually similar and more frequent alternatives. As we loop through each record in our test dataset, we gather detailed information about each token, including its misspelling probability and suggested corrections. The result is a data frame that organizes this information, prioritizing entries that need immediate attention. Looking ahead, this framework will pave the way for refining and enhancing the textual content in our dataset, preparing us for even deeper analytics or further processing in upcoming cells. By ensuring our foundational text data is clean and accurate, we set ourselves up for success in more complex analyses down the road. Cell 15. In this cell, we're setting up a foundational process for analyzing and correcting text data, particularly focusing on handling possible misspellings in descriptions and categories within a dataset. This is critically important because accurate text representation can significantly affect data integrity and the insights derived from it. The first part introduces the concept of tokenization and vocabulary building. By utilizing regular expressions, we create a set of rules to extract relevant words while filtering out those less likely to contribute meaningful information. We've defined a general English vocabulary, supplemented by specific domain-related terms, to ensure that our analysis is attuned to the context of business-related texts. This helps in identifying crucial keywords more efficiently. Next, we discuss how counts of tokens are built across specified columns in a data frame. The function will aggregate occurrences of each token, preparing a framework that allows us to analyze word frequency. This step is vital because it sets the groundwork for understanding the relative importance of each token, which informs both risk assessments and suggestions for corrections. One significant focus is the algorithm for determining the misspell risk associated with each token. Here, factors such as frequency within the column and token length come into play. For example, short tokens might be flagged as more ambiguous, which can be a red flag in identifying potential errors. This probabilistic approach helps in making informed decisions about which tokens might need additional scrutiny. The concatenation of the previously developed concepts culminates in the smart suggestion function, which aims to provide corrections for tokens deemed problematic. This function leverages fuzzy matching, comparing tokens against a reference vocabulary, ensuring that only meaningful corrections are suggested when there's sufficient justification based on similarity scores and frequency data. Finally, as we prepare to score the test dataset, we are essentially paving the way for a comprehensive table that reveals not just the tokens analyzed, but also their misspelling probabilities and potential corrections. The output will be a structured data frame highlighting both the risks and suggested fixes for each token, which can serve as a powerful tool for data cleaning and refinement. Looking ahead, the next cell will likely focus on how we can visualize these findings or further manipulate the resulting data frame to facilitate more in-depth analysis, incorporating the corrections into our workflow for improved data quality. Cell 16. In this cell, we are diving deeper into two different approaches to spelling correction, focusing primarily on why the second version demonstrates improved performance compared to the first. This distinction is significant, as it highlights key strategies in dealing with misspellings in a dataset. The first version of our spelling correction relied solely on existing entries in the dataset, which can be restrictive, especially when you have a limited quantity of data. It proposed corrections based only on frequent tokens, meaning that for a spelling to be suggested, it had to occur multiple times in the dataset. This inherently creates a barrier. If a correct spelling isn't present or doesn't appear often, the system struggles to generate viable corrections. In contrast, the second version expands our pool of correction candidates by incorporating a large reference vocabulary that includes commonly used English words and specific domain-related terms. This is crucial because now every potential typo has a valid spelling available for comparison. The introduction of fuzzy matching enhances the system's ability to identify words that closely resemble the misspelled input, opening the door for more accurate corrections. By no longer relying on the dataset alone to provide every necessary term, this approach mitigates the limitations experienced in the first version. One of the main takeaways is that while dataset-based correction excels in handling unique names or entities, like Wathali or Fabricam, which likely wouldn't exist in conventional dictionaries, dictionary-based methods are superior for standard language, as they offer access to established spellings. A hybrid system, combining the strengths of both approaches, tends to yield the best results in practice. Looking ahead, the next cell will likely explore how to implement this nuanced understanding of spelling correction into a practical application, where we can test and validate these theories with real-world data. Cell 17. In this cell, we're delving into the intricacies of managing text updates within a SQL Server database from a Python context. It's important to recognize that while it is technically feasible to push updates directly to the database, doing so without stringent governance can pose significant risks. The conventional approach in most organizations involves a clear division of responsibilities. Data science or analytics teams generate a reviewable report that includes not only the suggested changes, but also the confidence behind those recommendations. This ensures that any actions taken are based on informed analysis. The underlying logic here hinges on a structured workflow designed to safeguard the accuracy and integrity of the data. First and foremost, various pitfalls must be accounted for, such as the challenges posed by false positives in spell checking, where names like Sally and Sally can become contentious issues. Similarly, the impact on legal names or compliance documents cannot be understated. The ramifications of a single incorrect change can ripple through an organization, altering critical business meanings. Moreover, auditing and traceability become paramount when making changes to the database. It's essential to document what was altered, when, why, and by whom, as this not only upholds accountability, but also aids in conflict resolution should discrepancies arise. Upstream systems, like those encountered in a CRM or ERP context, can further complicate matters as they may overwrite corrections, creating a cascading effect that disrupts data reconciliation efforts. Typically, the database administration team doesn't engage in deciding what constitutes correct text. Still, they play a vital role in enforcing safe change processes, managing permissions, and overseeing the deployment of these updates. Meanwhile, data engineering is tasked with implementing the controlled pipelines that facilitate these fixes, ensuring that everything is carried out according to established protocols. On the other hand, data science focuses on building the logic and metrics that drive the scoring and recommendations for these updates. Looking ahead, the next cell is likely to build on these themes by exploring the actual processes and methodologies for implementing data changes safely and effectively, further emphasizing the importance of collaboration across teams. Cell 18. In this cell, we're conducting a quick sanity check to examine how well our misspelling detection system is performing. This is crucial because understanding the accuracy and relevance of our suggestions can significantly enhance the user experience in applications that rely on text input. We start by looking at the number of rows in our results data frame, which gives us a snapshot of our overall dataset. Next, we focus on the most relevant fields, pulling out the columns that detail the specific areas where misspellings were found, the tokens that were identified, and the suggested corrections, along with their similarity scores. By displaying the first 10 entries, we can get a clear visual sense of how the detection mechanism is working in practice, which helps us spot any discrepancies or unexpected outputs. The next part of the analysis dives deeper into the actual suggestions. We want to know how many suggested corrections are available at all. This check helps us assess the effectiveness of our system and ensure that it's generating useful suggestions rather than leaving users hanging with no guidance. Then, we define a threshold for similarity, setting it at 92. By focusing on suggestions that meet or exceed this threshold, we can filter the suggestions to only those that we consider to be highly relevant. The displayed output serves as an essential metric, helping us understand not only the volume of high-quality suggestions, but also the overall reliability of the misspelling detection system. As we proceed, we should keep an eye on the assumptions we are making throughout this process, particularly regarding the thresholds, as they can significantly influence the outcomes. Any unexpected values or low similarity scores might indicate potential areas for adjustment to enhance accuracy. Looking ahead, the next cell is likely to build on these insights. We may further refine our detection mechanism or even explore different thresholds and metrics to improve our overall approach. This ongoing iterative process is essential in developing a robust system that meets user needs effectively. Cell 19. In this cell, we're building proposals for updating our dataset, specifically focusing on rows in our test data frame that are relevant for record-based modifications. This is crucial for enhancing the quality of our data, as it targets areas where suggested fixes can significantly improve accuracy. The first part of the cell introduces a helper function that safely replaces words in a given text. This function uses regular expressions to ensure that only whole words are affected, making it case-insensitive and robust against partial matches. By having this tool in our toolkit, we can handle updates smoothly without worrying about inadvertently changing similar terms. Next, the main function kicks in. It takes several important parameters, including the test data frame, the results data frame containing suggested fixes, and some thresholds for determining which fixes are viable. One of the key steps involves filtering suggestions based on their similarity score and validity in specified columns. This ensures that we only proceed with suggestions that have a strong foundation and are relevant to our specific fields of interest. If there are no candidates that meet our criteria, the function early exits, returning an empty data frame with the appropriate structure. This is an important safeguard. It prevents unnecessary further processing and keeps our workflow efficient. For candidates that do meet our criteria, we group them based on their location in the data frame. This grouping allows us to systematically apply fixes, starting with those that have the highest similarity scores. The logic is designed to apply a limited number of fixes. This prevents overwhelming our data with excessive changes in a single pass, which could lead to potential inaccuracies. As we iterate through the suggestions for each cell, we keep a count of how many changes we make, ensuring we only document meaningful updates. If we do make changes that improve the original value, we append this information to our proposals list. The final output is a new data frame filled with these structured proposals, organized to prioritize the most promising candidates based on the number of fixes and their similarity scores. Finally, the transitions into the next steps will likely involve utilizing these proposals for actual updates or further analyses, paving the way for refining our dataset even more. This will be vital as we continue to enhance our data management practices. Cell 20. In this cell, we're setting up a robust framework for managing proposed changes to our data in SQL Server. This is vital because it allows us to safely handle updates by first staging them for review, thus minimizing the risk of errors that could affect our core data. The core logic involves creating two essential tables, one for storing proposed updates and another for auditing any changes that are actually applied. The first table, spell-check proposals, captures details about the proposed modifications, including identifiers for the affected records and the old and new values for each change. The variables like proposal ID, table name, and PK value play a crucial role in ensuring we can trace any proposal back to its source, making future audits straightforward. One of the standout features of this approach is the focus on safety and accountability. Any proposal remains pending until it receives formal approval, which is indicated by the approved flag in the proposals table. This means that even if multiple changes are suggested across different customer records, none will be applied without explicit confirmation. Meanwhile, the spell-check audit table allows us to maintain a complete history of applied changes, ensuring that we can trace back our steps if necessary. It's important to note that the code here is designed specifically for SQL Server, emphasizing not just how to structure the data, but also how we can implement controls to prevent haphazard updates. This method reduces the chances of conflicts or unintended data corruption, and it provides a structured way to manage data integrity across various updates. As we proceed to the next cell, we can anticipate implementing the mechanism for applying these approved proposals back to the main table. This transition will build on our existing safeguards, enhancing the overall reliability of our data management system. It underscores the importance of careful validation before any changes take effect, setting the stage for a streamlined and secure operation. Cell 21. In this cell, we're enhancing our data by integrating essential metadata columns into our staging data frame before preparing it for database insertion. This process is crucial to ensure that our data aligns with the structure expected in the database, which ultimately facilitates effective data management and accuracy during spell-check proposals. To achieve this, we start by creating a copy of the initial data frame. From there, we're adding 3 key columns: the name of the table, the primary key name, and the primary key value. It's important here to note the specific names we're using. In our case, saleslt.customer is set as the table name, and record ID is the chosen primary key for our test data frame. These designations play a vital role in later operations, especially when retrieving or modifying records in the database. Next, we refine our data frame to ensure it only contains the columns that our SQL staging table is designed to accept. These include both the metadata columns we've just added, as well as the actual data we want to track, such as column names, old values, new values, minimum similarity scores, and the number of fixes. This focused output helps streamline the data integration process and discards any unnecessary information, making our operation more efficient. The final step is to insert this neatly organized data into a SQL table named spell-check proposals. By using the toSQL function, we're not only appending our records if they already exist, but also ensuring that our script can handle creating the table automatically if it doesn't. However, it's worth noting that this behavior can be adjusted based on your needs, and for production environments, it's often better to pre-create the table in SQL to avoid any unexpected issues. It's key to remember that while the data frame manipulation is taking place in Python, the final SQL command should be executed within a SQL Server environment, not directly in Python. By observing these distinctions, you can prevent common pitfalls that occur when integrating Python with SQL databases. Looking ahead, the next cell will likely focus on querying the newly populated table within SQL to analyze the proposals and their effectiveness at spell checking. This transition will enable us to assess the changes we've made and their impact more thoroughly. Cell 22. In this cell, we're focusing on applying changes that have been approved for spell checking back to a designated database table while ensuring transaction safety. This process is crucial for maintaining data integrity, especially when multiple updates could breach consistency if not handled within a transaction. The core logic of the function revolves around pulling approved proposals from a specified database table. Here, we're particularly interested in records that have been marked with approval, and we filter these proposals using parameters such as the target table and primary key column. This helps to customize the function's behavior based on the specific table structure that we are working with. Once we've retrieved the approved proposals, we initiate a transaction with the help of SQLAlchemy's context management. This ensures that all updates occur within a transactional context, allowing for automatic rollback in the event of any errors. Within this block, we then iterate through each approved proposal and perform a guarded update. The condition used in a SQL update statement checks that the current value in the database matches the old value from the proposal. This prevents any unintended overwrite of modified data. If the update is successful, the function also logs this change into an audit table. The audit trail is vital for maintaining oversight and accountability, especially in environments where alterations to data are frequent. Notably, if no proposals are found, or if an update fails due to a primary key mismatch or outdated data, the code accounts for that gracefully. As we look ahead to the next cell, we can anticipate diving into how we might visualize the changes we've made, or even how to create reports based on the data in the audit log. This will not only offer insights into the changes applied, but also provide an overview of the impact these updates have had on the overall data structure. Cell 23. In this code cell, we are establishing a staging table in SQL Server, designed specifically for storing data quality fixed proposals, a crucial step for preparing and managing datasets effectively. The primary purpose of creating this staging table is to ensure that we have a proper structure to temporarily hold proposals before finalizing them, making it easier to manage data integrity and subsequent processing. The logic begins with checking if the staging table already exists in the database. If it doesn't, the script creates it by defining its schema, which includes essential fields such as customer ID, column names, old and new values, as well as some metadata to track when the proposals were created and who approved them. Each proposal is assigned a unique identifier, ensuring that we can accurately reference them. Next, we proceed to write the proposals into the staging table. Assuming that there are proposals available in the proposals df test data frame, the workflow involves copying this data to prepare it for insertion. During this transformation, we also add a few important columns, including the table name and primary key details, which are crucial for identifying the context of these proposals. The data frame is then filtered to the relevant columns before it gets appended to the spell check proposals table in the database. An important point to note here is the assumption that proposals df test contains valid proposals with necessary attributes filled appropriately, as any absence of data could lead to complications during insertion. Upon successful execution, the code prints a message confirming the number of proposals inserted into the database, providing immediate feedback about the outcome of the operation. This feedback loop can be incredibly valuable for debugging and validating our overall data handling process. Looking ahead, the next cell is likely to delve into how these stored proposals can be manipulated or reviewed within the database, enhancing our understanding and control over data quality efforts. This transition will keep our focus on the practical implications of the staging table we just created, paving the way for further analysis or actions based on these proposals. Cell 24. In this cell, we're discussing the conditions under which it's reasonable to automatically apply fixes to data, particularly in the context of handling free text descriptions. This is important because while automating data correction can save time, it can also introduce errors if not done carefully. The core logic emphasizes a few key criteria. First, the data field must involve free text descriptions, meaning we should avoid fields that contain identifiers, names, or any sensitive regulated information. This ensures that we minimize the risk of corrupting important identification data. Next, we should only apply changes when we're highly confident in their correctness, which, in this case, means a similarity score of at least 95%, and a match with both a dictionary and domain-specific vocabulary. This level of confidence helps ensure that our changes are purposeful and reliable. Another critical aspect is the implementation of guardrails to protect the integrity of the data. These could include applying changes only to open records. Think of these as records that are not locked or finalized, or restricting updates to only recent entries. Additionally, we need to be careful not to alter tokens that appear to be codes, such as alphanumeric strings, IDs, or email addresses. These are often crucial for maintaining data functionality and should remain unchanged. Moreover, an audit trail is vital. By keeping track of what was changed, what the old values were, who made the change, and when it was made, we create a transparent process that allows for accountability and traceability. The workflow suggested is staged, meaning we first draft the changes to a staging table for review and approval, rather than applying those changes directly. This helps mitigate risks, as it allows for manual oversight before the updates are finalized. If these precautions can't be guaranteed, the consensus is clear: we should treat automatic updates as too risky. Looking ahead, the next cell will likely explore the practical implementation of this workflow, possibly covering how to structure the staging tables and the review processes that follow. This ensures we maintain a robust data integrity strategy while still leveraging the efficiency of automation. Cell 25. In this cell, we're exploring how to integrate an AI layer locally to enhance our data processing without relying on cloud services. This is particularly significant because it allows us to maintain data privacy and reduce costs while still leveraging advanced models. The key idea here is to use local tools, like sentence transformers, for tasks such as clustering suspicious tokens. This means we can analyze how related various terms are to one another within our dataset, enhancing our ability to identify potential errors or inconsistencies. Another approach mentioned is utilizing a local language model to evaluate whether specific entries, like Sally, are likely typos of Sally, especially by examining contextual clues from related columns, such as names and addresses. However, it's crucial to note that while these AI methods can be powerful, there are simpler, often more effective ways to tackle tasks like misspelling detection. For instance, relying on frequency analysis, similarity checks, and reference lists tends to outperform complex models in this particular area. Additionally, these traditional techniques are often not only more cost-effective, but they also offer greater transparency in how decisions are made. This point is emphasized multiple times throughout the cell, underscoring the importance of recognizing that AI is a tool, but not always the best fit for every task. After establishing this foundation, the next cell will likely delve deeper into implementing these local models or explore additional alternatives, continuing our journey into effective and efficient data management strategies. Cell 26. In this final cell, we're wrapping up the work we've accomplished throughout this Jupyter notebook. While it might seem simple to just conclude, it's actually quite crucial as it ensures that all our previous analyses are coherently tied together and understood. As we finish, it's a moment to reflect on the data processes we've executed and the insights we've garnered. Throughout this notebook, we've navigated through various techniques, examined numerous datasets, and likely encountered both challenges and revelations along the way. This cell acts as our bookend, signifying not just an end, but also the culmination of our efforts in understanding the data. It's important to criticize and discuss the insights we've derived. We could consider what assumptions might have influenced our conclusions and acknowledge any limitations of our analyses. Throughout our journey, we've been careful to validate our findings, ensuring that the insights we gained are reliable and meaningful. Moreover, it's also a moment for you to think about the implications of the work you've done. How might these results be used in practical scenarios? Are there questions that remain unanswered, or alternative methods that you might apply in the future? By reflecting on these aspects, we not only solidify our understanding, but also pave the way for further inquiries. Transitioning into the next stage of your learning journey, it's worth considering how you could apply these methodologies to new datasets or even different contexts. The analytical skills you've sharpened here are just the beginning. As we move forward, you can take these principles and explore fresh datasets, continue refining your techniques, and perhaps even challenge the insights we've gathered with new questions and data.